Hello everyone, we're Team 4 and we will be presenting our analysis and redesign of personal humidifiers. For some background information, USB-powered humidifiers are equipped with an ultrasonic transducer that converts water into tiny droplets, which are then dispersed into the air using a fan. The mist is blown into the surrounding area through an outlet. The device consists of a metal outer casing covered with a plastic cap, which contains a PCB and a water level sensor. The primary customer group for this product is people with nasal congestion issues, looking for a quick relief or at-home therapy. The overall focus is on the overall wellness and comfort of living. The secondary customer group is people looking to increase the quality of their indoor gardens and enhance plant quality. These two customer groups form the framework for our two product variants. The product has an estimated demand of 8 million devices per year with a target annual production volume of 350,000. And it also has a compound annual growth rate of 4%. Humidifying air is the main function of the personal humidifier. This task is accomplished through the primary basic function of vaporizing water, which is further supported by two secondary functions, containing the water and adding heat. Furthermore, the second main function is creating mist, which is then followed by the two secondary functions, containing steam and distributing steam. Additional functions fall under the categories of assuring dependability, convenience, product enhancement, and pleasing senses. As can be seen, most components in the matrix have either one function or between 2 to 3 functions mapped by the FAST diagram. However, the prevent burns function has 5 functions mapped, which could lead to an inefficiency. From the table, we also see that a few components are listed under multiple functions, which could call for part redesign or consolidation. As seen in the table, the only function difference between the customer groups is the control of steam output. This function is performed by the tank cap, which is the module of the design, while the rest of the parts are the platforms. This means that the tank cap needs to be redesigned through DFA. The difference in the two variants is the diameter to allow for more or less steam output. The change in the dimensions for both variants have no effect in the way it is mounted and aligned with the tank cap and the tank housing. The original design sequence runs parallel due to putting the tank cap as the first item. In the modified assembly, the tank cap is moved further down the assembly sequence, allowing the sequence to start with the mid-body housing. Following the interim report, the tank cap was redesigned to become a platform part. We analyzed the assembly to find the highest impact parts on the overall assembly time. Looking at the highest times of non-purchased parts, the tank cap was an obvious choice for us and can also be seen in the quad chart as a part for redesign. The mid-body base ring requires fasteners, which brings its time up to 61.8 seconds and therefore can be redesigned. As we can see, the mid-body base ring distributes steam while the tank cap contains steam. Starting with the mid-body base ring, the original design took 61.8 seconds to attach the rest of the assembly. We improved the design for manual assembly by reducing part variety, preferring snap fits, eliminating fasteners, and reducing part counts. This redesign had no major effect on the part function, and no major effect on the manufacturing cost. It saved us $0.025 per part, and we were able to reduce the assembly time to 3 seconds from 61.8 seconds. Continuing with the tank cap, the original design took 5.5 seconds to attach to the rest of the assembly. The red arrows point at the slots around the part that were redesigned. We improved the design for manual assembly by providing locating features, adding features for easy installation, adding features to facilitate orientation, and preferring snap fits. As well, there was no major effect to the part function, but there was a slight effect to the manufacturing cost as it saved us $2.21 per part, and we reduced the time from 5.5 seconds to 3.5 seconds.
For automated assembly, we selected the subassembly of the sensor shield, sensor rods, and the wick filter. The function component map matrix shows that the sensor shield and rod share all functions, which provides an opportunity for part consolidation. The initial design of the subassembly is shown. The subassembly costs $1.46 to automatically assemble. The redesign of this subassembly consisted of condensing the two sensor rods and sensor shield into a single part, reducing the subassembly to a total of 2 parts. This redesign also avoids adjustments during assembly. The product being less adjustable does not affect the product function in any way. The new assembly cost for this redesign is 83 cents, which is a decent decrease compared to its original cost of $1.46.
We will now move on to the process selection for the tank cap. As visible here, the major function of the tank cap is to contain steam. Here are the critical dimensions for the tank cap. The most important are the diameter of the central hole, which determines how much steam is dispersed by the humidifier, as well as the sizing of the holes and the slots along the periphery, which facilitate integration with other components such as housing, diffuser cap, etc. A tolerance of plus minus 0.1 mm was chosen for this part, which is typical for any 3-axis lathe. The tank cap was to be made out of an aluminum alloy. We narrowed down the manufacturing processes to powder method and machining based on the shape, weight, section thickness, tolerance, surface finish, and the batch size. Finally, we decided to machine the tank cap. There were a number of design flaws in the original tank cap, which were pointed to us by DfM Pro. The most critical of these were deep holes, hole intersecting cavities, and tool accessibility. We employed analytical calculation method to determine the machining cost of each part. We concluded a material cost of $2.72 and a machining cost of $10.55, amounting to a total of $13.27. From the suggestions given to us by DfM Pro and the principles we have learned throughout this course, we were able to employ some critical redesigning to facilitate machining of this part. We reduced the thickness and depth of the holes. We added radius to the internal corners, negated parts which required drilling on inclined surfaces, and avoided any undercuts. These changes had no major effect on the functioning of the part, but we were able to reduce the cost of production by 16.6%, going from $13.27 to $11.06 per part, according to our analytical calculations. As per the codes given to us by Hub, we could see a 12.7% reduction in the cost after compensating for their profit margin, as the cost reduced from $6.14 to $5.36. These are the critical dimensions after DfM was performed on this part. As you can see, none of the important dimensions are changed.
So let's take a look at the process selection for the mid-body base ring. The main function for the mid-body base ring is to distribute steam. Here are the major dimensions for the mid-body base ring. We selected a tolerance of 0.3 millimeters, and the dimensions are critical to ensure the proper alignment of the mid-body base ring with the tank cap and the tank housing. In terms of process selection, we took ABS to be the main material, and we were able to narrow down our processes to machining and injection molding. And for the purposes of this part, we selected injection molding. We analyzed the part using DfM Pro for the design for manufacturability aspect. We were suggested 4 main changes from DfM Pro. We also calculated the total cost per part, which came out to be $0.128 per part. And this was including the operator cost, mold cost, and the material cost. We were able to redesign the part to add the 4 changes, which were adjust rib parameters, add draft angles, keep uniform wall thickness, and reduced mold wall thickness. We also updated the cost calculation, which came out to be $0.103 per part. There was no major effect to the part function and a slight change, but not much effect to the manufacturing cost with a reduction of $0.025. There were no major changes to the critical dimensions of the part, just the addition of a snap fit instead of the fasteners. In terms of our product service system, our goal was to improve customer service experience and reduce the negative impact on the surrounding environment. We wanted to do this by implementing end-of-life recycling, that is recycling products at the end of their life cycle, including reusing components, employing sustainable manufacturing practices by energy efficiency and reducing waste, improving customer service and support, and using data collection and customer feedback to help improve our product experience and product functions in the near future. To summarize, we were able to reduce the manual assembly time for both the mid-body base ring and the tank cap. We were able to save on the assembly time and cost for the sub-assembly of the water sensor components. And using design for manufacturability, we were able to help reduce the manufacturing costs for both the tank cap and the mid-body base ring. Our final critiques include changes to the tank cap to help further lower the manufacturing cost, as well as additional DfM required for non-selected parts.